This is Chapter 35, Related Rates, Part 2. And here we have another ladder question. And so again, we have a ladder that's 10 feet long, is sliding down the wall. In this problem, we're asked to find the rate of change of theta. Now, again, when you can, draw a picture, and you want a well-labeled picture. You want to label the parts of your picture that you're either given information about or asked information about. We're given information about the length of this side, so we label that with a variable. We're given information about, or we're asked information about theta, about this angle, so we label it theta, and we're told that the ladder is 10 feet long. Again, the length of the ladder is not changing, so I put a constant here. This is changing, so it's a variable, and the angle is changing. As the ladder slides down the wall, this angle decreases. So the angle is labeled with a variable. Even though we're given at some point in time that x is 5, x is not always 5, so I don't put a 5 in the picture. Sometimes it's helpful to draw a second picture with the constants in it. I tend not to do that. So now from our picture, we see that sine of theta is opposite over hypotenuse. So sine of theta is x divided by 10. Just to make the algebra a little bit simpler, I multiplied both sides by 10. This is an optional step. You don't have to do this. And it's a related rate question. We're being asked about the rate of change of theta. So we take the derivative with respect to time of both sides. So derivative with respect to t of 10 sine theta, derivative with respect to x of t. So we use implicit differentiation. The derivative of sine is cosine, so we have 10 cosine theta d theta dt. Theta is a function of time. Theta depends on time. We're taking the derivative with respect to our time variable. Even though we don't actually have theta explicitly defined in terms of time, it is a function of time. Same thing with x. X is a function of time. What x is depends on how much time has passed. What theta is depends on how much time has passed. We just don't have x and theta explicitly defined in terms of time. We have them implicitly defined in terms of each other. Actually, yes. Okay. So we have 10 cosine theta times d theta dt is dx dt. Now, we have three variables. We have theta, d theta dt, and dx dt. And as I said before, we have to have been given enough information to find two of those variables. Here's the thing though. For this one, we don't actually need to know what theta is. But we do need to know what cosine of theta is. Now, we're told that at this particular time, x is 5. We want to find the rate of change of theta with respect to time when x is 5. So, if x is 5, what do we have? We have a 1 square root of 3, 2 right triangle. So we have 5 square root of 3, and then 10. So that is our 1 square root of 3, 2 right triangle, with our scalar being 5. So the length of this side is 5 square root of 3. Cosine of theta is adjacent over hypotenuse. So cosine of theta is 5 square root of 3 divided by 10. d theta dt is what we're looking for. dx dt we were given. We're told that the ladder is sliding down the wall at a rate of 3 feet per second. Again, x is decreasing, that's why our rate of change is negative. So now we have a constant times d theta dt equal to a constant. Solve for d theta dt. It's negative square root of 3 divided by 5. So theta is changing at a rate of square root of 3 divided by 5 radians per second at the time when x is 5.